Hi, welcome to Intermolecular Forces, Solids and Liquids. My name is Dr. English. Today we're going to be talking about the solution process. Specifically, we're going to be looking at some definition of terms, ion-dipole interactions, enthalpy changes in solution formation, trends of solution formation, examples of solutions. Let's start out by talking about the solution process. A solution is a homogeneous mixture of a solute and a solvent. Solutions may be gases like air, liquids like food coloring and water, or solids like alloys of metals. Each substance present is a component of the solution. The solvent is the component present in the largest amount. The other components are called the solutes. In the process of making solutions with condensed phases, intermolecular forces become rearranged, and we're going to see that in a moment. So the little drawing that I have over here is a sad-looking beaker. We have our solvent, which is the blue liquid, and our solute, which is represented by these little dots. Now let's consider sodium chloride, which is going to represent my solute, dissolving in water, which will be my solvent. Water molecules orient themselves on the sodium chloride crystals. So at the very beginning, we have this diagram, which represents sodium chloride crystals as a solid. Hydrogen bonds between the water molecules have to be broken because initially these water molecules, which we see already arranged around these ions, but originally these water molecules are together. So we've got to break them apart first. Then the sodium chloride dissociates into sodium ions and chlorine ions. Ion-dipole forces form between the sodium ions and the negative end of the water dipole. So we can see here in our little representation that this sodium ion, which is represented by this blue sphere, all the oxygen ends are oriented towards this sodium ion. A similar ion-dipole interaction formed between the chloride ion and the positive end of the water dipole. So over here, there's my chloride ion, which is negatively charged, and the positive end of the water molecule, which would contain the hydrogen, is oriented towards that chloride ion. Such an interaction between the solvent and the solute is called solvation. If water is the solvent, the interaction is called hydration. Energy changes in solution formation. There are 3 steps involving energy in the formation of a solution. The first step would be the separation of the solute molecules, and that's going to require some energy. The next step would be the separation of the solvent molecules. So if it was water, it'd be separating the water molecules from each other and breaking those intermolecular forces. Now, of course, these are happening simultaneously. And finally, the formation of the solute-solvent interactions. So that's going to be represented as delta H3. We define the enthalpy change in the solution process as our overall heat of solution is equal to the sum of the interactions from separation of the solute molecules, the separation of the solvent molecules, and finally the intermixing of the solute and the solvent. The heat of solution can either be positive or negative depending on the intermolecular forces involved. To determine whether the heat of solution is positive or negative, we consider the strengths of all the solute-solute, solvent-solvent, and solute-solvent interactions. Breaking attractive intermolecular forces is always endothermic, so therefore delta H1 and delta H2 are going to be positive. Forming attractive intermolecular forces is always exothermic. Therefore, delta H3 is always going to be negative. It is possible to have either this situation where my heat of reaction for the forming of attractive forces is greater than the breaking of attractive forces from delta H1 and delta H2, or that delta H3, the forming of attractive forces, is going to be less than the breaking of the attractive forces for delta H1 or delta H2. Either of these situations can occur depending on what's involved. Let's look at 2 examples. Magnesium sulfate is added to water, and that's going to have a heat of solution that is exothermic, negative 91.2 kilojoules per mole. We compare that to adding ammonium nitrate to water. That's going to have a heat of solution of positive 26.4 kilojoules per mole, which is endothermic. So either of these situations can happen. How can we predict if a solution will form? In general, and of course not always because we're seeing it right here, but in general, solutions form if the heat of solution is negative. Therefore, it's an exothermic reaction. If the heat of solution is too endothermic, a solution is not going to form. The general rule of thumb is that polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. Many times, especially in Regents chemistry, you were taught like dissolves like. So we look at differences or similarities in the overall molecular polarities of molecules, and that will help determine whether two substances will dissolve or not. Consider the process of mixing sodium chloride in gasoline. Only weak interactions are possible because gasoline is nonpolar. We're going to see London dispersion forces occurring within gasoline. These interactions do not compensate for the energy required for the separation of ions from one another, because of course sodium chloride is going to be held together by the electrostatic forces of positive and negative ions that exist within the ionic crystal. The intermolecular forces that gasoline possesses are very, very weak. They're not going to be able to overcome those intermolecular forces in sodium chloride. Therefore, sodium chloride does not dissolve to any great extent in gasoline. Now let's consider the process of mixing water in octane. Water has strong hydrogen bonds as the force of attraction between the water molecules. The energy required to break these hydrogen bonds is not compensated for by the interaction between water and octane. Again, water and octane do not mix. And we can see this very cool image here of water and octane attempting to mix together, and it's not happening. So what did we learn in this tutorial? We talked about some definitions of terms like solute, solvent, and solution. We talked about ion-dipole interactions. We looked at enthalpy changes in solution formation. We talked about trends of solution formation, and then we looked at some examples of solutions. Need more help? Feel free to contact me. Have a great day.